Hi, good morning. Welcome to the third session on subspace topology. Today we are going to look at some set theoretic results concerning subspace topology, and we will possibly end up with a very beautiful application or a perspective about convergent sequences. I hope you all like it. Okay, so let's get started. Yeah, so you can read all these things, subspace topology, but the most important thing is you should look at my YouTube channel. And there is the way the videos are listed are not very good in YouTube channel. So about 9 months ago itself I started publishing a list of videos, and also the list of videos gives a proper order within a particular theme, be it real analysis or linear algebra or topology or metric space, the particular sequence in which you can watch the videos as a regular course. Okay, so please look into this article, look for the article list of videos, and you can download it from here. And my hope is that I will periodically update. Okay, for 3-4 months I didn't update, but hereafter I plan to update it at least once a month, so that it will be easier for beginning students. Okay, because it's really cluttered. Even I cannot find out the video which I want in my own channel. Yeah, anyway, that's enough about griping. Let's get into our work. Okay, so what are the results we want to look at is the following. Let me just quickly recall. So I have x tau topological space, and A is a subset of X. Okay, and this is, since I myself I'm coming back to this after a long time, let me recall what is the subspace topology. Subspace topology is U intersection A, let me call it perhaps V intersection A, so that V is in tau X, tau or tau X. Okay, right, all of you must have seen this is a topology on X, on A, sorry. This is called subspace topology. Okay, so what are the things I want to prove today? Yeah, before I prove today, let me just recall something which we did when we dealt with the co-countable topology. Okay, if X is with co-countable topology and A is a subset of X, then we proved tau A is also co-countable topology. This was in subspace 2. Okay, and we just needed a set theoretic observation to prove that. If you want to say a theoretic lemma, okay, what did it say? Suppose I have something like this is my X and this is my A. Okay, this is my A and this is my, let us say, U. Okay, and suppose my U comes from, okay, this is my V. This V is also included, right? So what we have is my U is a subset of A, but U is actually V intersection A. Then we said what is A minus U. Okay, what it said is look at X minus B and intersect it with A. Pictorially it's very easy, remember that. Okay, that's a very crucial thing which we are going to use again today. So let me quickly go through a proof. Suppose A, so let me prove this way. So let A belong to A minus U. That means A is not in U. But what is U? V intersection A. Therefore what does it mean? Since A is already in A, okay, this means A is not in V. But remember, A is in A and here, therefore this means A is in A and A is in X minus V. That means A is in X minus V intersection A. Is that clear? With just set theory, many times when people do not learn how to work with this kind of thing, I'm just repeating. Okay, this is what I also always do till I become very absolutely confident. Even a small thing which I was saying earlier, okay, I repeat it so that I become very confident. Any time I can go through a proof and work it out. Okay, that's the reason why I'm doing it. Okay, so that you will also understand. Whereas I could simply say I had already done it, recall it, and then go ahead. But this I usually see that it's not done by people, so you may have. Okay, so now I have to prove the other way around. So let x belong to x minus b intersection a. So what does this mean? This means x is in x minus b and x is in a, but this means x is not in b and x is in a. Yeah, right. So what does this mean? This means x is not in u, because u is b intersection a. Therefore if x is not in b, x is certainly not in a, right? Therefore x is in u, x is not in u and x is in a. What does this mean? This means x is in a but not in u. So I proved it. Therefore I have proved a minus u, that is complement of u in a, is complement of b in x intersect the a. Okay, pause, review, proceed. Notice that our earlier picture already said that. Yeah, because what is this? A minus u is this, right? And what is x minus u? X minus u is going to be this. And intersect also with a, then you get it, right? Okay. So what are the things we want to prove? Let me call it a theorem, because these are the very basic results about subspace topology. You may need them often. That's why I call it a theorem, even though they are all very simple exercises in subspace topology. So let x be a topology space, and A is of course a non-empty subset of x. Tau A is a subspace topology on A. Right? So what are the things I want to prove? The first thing is, suppose A is open. Okay, assume that A is open. Okay, then U, a subset of A, is open in A, that is U belong to tau A. If and only if U belong to tau, that is U is open in X. Okay, let us go through the proof. There are 1 or 2 or 3 or 4, I don't remember as I go along, but this is one. The theorem may consist of 2 or 3 points, 2 or 3 results. Okay, but it's easier if I prove the result here itself rather than just listing all of them and then proving one after the other. That's what I would do in a book, but here it is easier for me to do it like this. Okay, so let us look at that. So let us assume U is in tau A, right? Now since U is in tau A, right, there is a V in tau, so that what U equal to V intersection A, right? Now B is in tau A and A is open, therefore U, that is also, sorry, tau x, tau, simply tau, sorry, and A is open in X, therefore A belongs to tau, therefore this intersection also belongs to tau, but the intersection is U. Therefore I have proved U in tau A implies U is in tau. Okay, just make sure you understand. I'm going fast because these are all very easy. As I said, for a reasonably good student, this should be a trivial exercise. You should not look for a proof in a book or from me. Okay, yeah. Now let's assume that what is that? Yeah. Now suppose U is a subset of A, but U is already in tau. Then, right? Then what is U intersection A? U intersection is U, right? U is already in A, therefore U intersection is U. But remember, this is in tau, this is also in tau, therefore this is in tau. There. Yeah. So what do you think I have proved? Oh, sorry, I have to put the other way around. I'm sorry. Okay. So let u is in a subset of A and let u belong to tau, then I want to know whether you belong to tau A. This is a question, right? But that's easy. That's a proof I wanted to give. That's easy because u is nothing other than u intersection A, because u is a subset of A, therefore u is intersection A, right? But since u is in tau, okay, this means by the definition of subspace topology, u, which is u intersection A, that should be in tau A. Are you following? Yeah. To prove u is in tau A, what should I do? I have to produce an open set V in X so that u equal to V intersection X, V intersection A. But what is the V I am looking at? U itself. That's it. Do you follow that? Okay. So pause, review, proceed. So what is the counterpart of this? Can you guess? Let's look at what did I prove. If A, assume the subspace, that is the subset A is open, then I am looking at subspace topology. If U, a subset of A, is open in A, that is U is in tau A, if only U is in tau X, tau. What should be the counterpart? What should be the dual question, similar question, analogous question, related question you should ask? Remember, I always insist that whenever you do something, ask yourself questions. What should be the question you should ask? Yes, you are right. The question is, suppose assume A is closed. That is tau, that is, yeah, X minus A belong to tau, right? That's what it means by A is closed, right? Okay, good. Now suppose B is a subset of A and B is closed in A. That means what? B is closed in the subspace topology. What does that mean? That means you took a look at A minus B, then it belongs to tau of B. That's all it means. You understand? Right. Now what is that you want to say? So we are not saying this. Keep this aside. So can you make a guess? What should be the result? Keep this aside, okay? Ignore this. Suppose B is a subset of A. So we are looking at analogous of the first question. So what do you want to say? You want to say B is closed in A if and only if B is closed in X. This is what I want to prove. Do you see the analogy? In the earlier case, I assume A is open, U is a subset of A, U is open in tau A, if only U is open in X. So the analogous question is, suppose A is closed and B is closed in the subspace topology of A, if only B is closed in X. Isn't it beautiful? Remember, these two facts will be very often used when you want to look at subspace topology in set theoretic way. Okay, so learn this well. The proofs are easy. Okay, but I will make the life easy. Okay, let us wait. Okay, wait for a few minutes. We will attend to it later. Okay, now let's look at the subspace topology tau A. How did we do? If I have U in A, I said U belong to tau A if only if there exists V in X or tau, so that U is V intersection A. Right? This is the definition of subspace topology. Okay. Now let me ask you a question. Suppose F is a subset of A. I want to say F is closed in A. That is in the subspace topology. Okay. Can you guess what you would like to say? If only if there exists a closed set C subset of X closed in X and my F is C intersection A. Notice that is exactly similar, analogous, right? I want to say F is a closed subset in A if and only if there is a closed set in X, so that my F is C intersection A. keep the picture which I drew earlier in mind and look at the subspace topology definition, you see it's a perfect analogy. Yeah, if you grant me this, the earlier result is obvious. Okay, this is the third thing. This should actually be 3, but it should be made 2, therefore 2 becomes 3. Okay, let us, but this proof is easy. How many of you know this proof is easy? Okay. This is where our set theoretic lemma comes. How do I do? Suppose F is closed in A. That means U, which is A minus F. Okay, open in A. Right? Therefore, my U is what? V intersection A, where V is open in X. That's our definition. You understand that? Yeah? Please pay attention. I am going to use my set theoretic lemma. What did I say there? I may forget the notation. Let me just to make sure I remember the notation. Yeah, U. Yeah. All right, let's look at it. So U. Therefore, what is U complement in A? That is A minus U. That is nothing other than take V complement in X and intersect with A. Right? This lemma I can use now. Right? Therefore, what is F? F is A minus U. But this A minus U I know is nothing other than X minus V intersection with A. But remember, V is open in X, therefore this is closed in X. Okay, therefore I can take this to be the subset C. Please pay attention. Have you understood? So I start with the closed set F in A. I proved there is a closed set C in X, so that F is C intersection A. Right? Okay. Now suppose F is a set subset such that there exists a closed set C in X so that F equal to C intersection A. What do I want to prove? I want to prove F is closed in X. Okay, please pay attention. Okay, because this kind of logical thinking, I mean, is what not encouraged. Teacher keeps on writing notes, you take it down. Right? So what did I prove earlier? F is a closed subset of A. Then I said there exists a closed subset C in X so that F equal to C intersection X. Now what do I want to prove? I want to prove the converse. Suppose F is a subset of A so that I can find the closed set C so that F equal to C intersection A. Then I have to prove F is closed in A. Right? Right. Very good. Now let's look at this. Notice that F is C intersection A. So again take U equal to A minus F. Right? So this is what? U is nothing other than A minus F. Right? But this we know what it is. Since F is C intersection A, therefore my this one is X minus C intersection A. This is by set theoretic lemma. See, if you keep the picture, the symbols will not affect you. Many of you will remember something like a U, A, B, X, etc., V. You will get confused. You should not. Okay, they are all symbols to write the proof, but the basic picture should be there. So I have a subset F which is C intersection A. Therefore, its complement is take the complement of C in the full space, intersect with A. So I got it. Right? Now what do I know about this? Since C is closed in X, okay, this is closed in X, therefore this is open in X. Therefore my U is open in A. Right? But its complement therefore is closed in A, which is F. Yeah? So F, which is A minus U, belong to, is closed in A. Are you happy? Pause, review, proceed. So what have we shown now? We have shown the following, that A is a subset and F in the subset of A, then F is closed in A if only if there exists C closed in X, so that F is C intersection A. Yeah, this is what we prove. This is what I call 3, actually should go as 2 anyway. Okay, so what is 2 now? 2 said the following: if A is closed in X, then F a subset of A is closed in A if only if F is closed in X. This is what we wanted to prove. Now that's very obvious one. If you notice that, suppose F is closed in A, right? That means what? There is a C closed in X, so that F is C intersection A. Right? Okay. Now notice that C is closed in tau. It's not in tau, okay? It's closed in tau, okay? It's closed in X. A is also closed in X by hypothesis. Therefore, intersection of finite intersection of closed sets is closed. Therefore, this F is closed. This implies F is closed in X. Yeah? So, if A is a closed set, F is closed in A if only if, that implies F is closed in X. Converse is again easy. Suppose F is closed. F is a subset of A, but F is closed in X. Okay, right? Then what is F? F is F intersection A. Right? Now what do I know about F? F is closed and A is closed. Right? Therefore F is closed in A. Why it's closed in A? Because I have shown F as intersection of a closed set C with A, where my C is A. Do you remember what was my 3? 3 said if F is closed, if only if there exists C which is closed, so that F is C intersection A. Okay, so have I produced such a C? Yes. Take F itself as a C, then F intersection A is F, because F is a subset of A. But my F is closed in X, A is closed in X, therefore F is closed in A. Is that clear? Pause, review, proceed. Okay. So there is a fourth one which is usually not done, but I find somewhat very useful, because at many of the theorems what you know use it is something about an adherent point. Let me say it, okay, that will be easier. Suppose again A is a subset of X, okay, B is a subset of A, let X be in A, then X is an adherent point of B in A if only if X is an adherent point of B in X. This actually comes from our last thing. In fact, I can use 3 to prove 2 and 3 also. But let's not worry about it, okay, don't forget it. These are all very small things. Get a straight proof and be happy, and revise the proof twice or thrice, so therefore you will feel confident you can get the proof. After that, what you need is only those facts to apply elsewhere in your life. Okay, what is that I want to say? No, do you understand this? Right? For example, if I take 0, 1, now 0 is an adherent point of this set, where B equal to A itself, okay, or B equal to, let us say, 0 half, okay. This 0 is an adherent point, but what we are saying is X already must be in A if it is an adherent point of B in A. Remember, X is a point of A. That's very crucial. For example, when you prove uniqueness theorem, identity theorem for analytic or holomorphic functions, etc., you have to deal with an adherent point of the 0 set in the given domain. Okay, these are the subtle points. Many times teachers don't explain very well, and students do not appreciate the subtleness. Please go through this. So what I am saying, X is already in A and B is a subset of A. Then I want to know, now with the subspace topology I can ask whether X is an adherent point of B. right? Then I want to say that happens if and only if it's an adherent point of B in X. Consider B as a subset of X. Then now notice that for this B, all the adherent point is already closed. This set is already closed. B is closed in A because it is intersection of, for example, minus of intersection with A, right? Therefore B is already closed. Therefore all the adherent points of B are B points of B, nothing more. But when you consider B as a subset of R, then 0 is an adherent point of B. So it may have adherent point elsewhere. So therefore what we are saying, again and again repeating, don't get bored and don't get irritated. Okay, this is a very subtle point. So B, we look at X in A. If it's an adherent point of B in A, then it's an adherent point of B in X. On the other hand, there may exist a point X in X which is an adherent point of B, but it may not be in A. Look at this example. Okay, don't worry, these kind of questions are never asked, but on the other hand, if you learn these things, subtleties well, you will feel very confident. Okay, let's go back to the proof. Okay, so let us assume X is an adherent point of X is in A, and adherent, maybe I will use A so that it will be easier. A is an adherent point of B in A, right? So this is my X and this is my A and this may be my B. Okay, this is an adherent point. Okay, then I want to say A is an adherent point of this. Now let us look at, so I want to know whether A is an adherent point of B in X, right? That means what? That means give me an open set B in tau so that A belong to B. Give me an open neighborhood of A in X. Okay, then what do I have to show? I want to show A is an adherent point, that is, give me any arbitrary open neighborhood of A in X, then it should intersect B. This should be non-empty. This is what I have to prove. Right? Is that clear? But let us look at it. Now let us look at this. Let us look at B intersection A. Right? Okay, there. Remember, this is A already is there in B. Therefore, A belongs to B intersection A. Therefore, this is an open set in A. Right? Now, what do I know? This is an open set in A, and A is an adherent point of B in A. That means, call this as U. This is an open neighborhood of A. Therefore, U intersection B should be non-empty. But what is U intersection B? That is B intersection A intersection B is not empty. But A intersection B, this is B intersection B, this is non-empty. You follow that? So I wanted to prove B intersection B is non-empty. How I proved it? Yes, because B intersection B is same as B intersection A intersection B, but since A is an adherent point of thing, this is your U, this is non-empty. Therefore, this becomes non-empty. Okay? So what have you proved? I have proved A in A adherent point of B in A implies A is an adherent point of B in X. This is done. Converge is again equally easy. Suppose A is in X, A is an adherent point of B in X. That means what? What does this mean? This means for every U in A, so that A belongs to, I usually use B, right? So that B is an open neighborhood of A, B intersection B is non-empty. This is what it means. Right? Now what do I have to do? I want to prove A is an adherent point of B in A. That means what? You give me any open set U in tau A, so that A belongs to tau A. Then what do I have to show? U intersection B is not empty. Right? If I want to show A is an adherent point of B, you give me any open set in A, that is in the subspace topology. It should intersect B. Right? Okay. Now u is in tau A. What does it mean? There is a v in tau, so that my u is v intersection tau, v intersection E. Right? Yeah. Okay. Now what do I know? Now you notice that A belongs to B as well as in A. This is the place where we are using A is in A. You see that? We are using the fact A belongs to U. Because B is in, are you following? B is in, yeah? B is in A because I am looking at V is an open neighborhood of A in X. Right? A is already an element of A. Therefore it belongs to U. Okay. Now U is where? In tau A. Yeah. So what do I know? U intersection, because A, by hypothesis, A is an adherent point of B in A. Therefore what do I know? U intersection B is not empty. But what does this mean? This means, what is B? What is U? U is V intersection A intersection B is not empty. Right? But what is this? B is a subset of A, therefore that means B intersection B is not empty. Yeah. So, are you following? So I have to prove. Sorry, let me be a little more focused. My assumption is, I forgot what I am assuming. A is an adherent point of B in X. Okay. Okay, I want to know whether it's an adherent point of B in A. So what does that mean? So let U be in tau A, so that A belongs to U. So what is that I have to prove? I have to prove U intersection B is not empty. This is what I want to prove. Right? But U is in tau A, that means there is a V in tau, so that what do I know? U is V intersection A. Right? Okay. Now remember, what is our assumption? A is an adherent point of B in X, and B is an open neighborhood of A in X. Therefore, okay, I know B intersection B is not empty. Right? Is that clear? Yeah. Now what is that I have to prove? I have to prove U intersection B is not empty. Yeah. But remember, U intersection B is B intersection A intersection B. Because B, U is B intersection A. Right? Now what do I know about A? This is the place where I am using A is in A. Right? Since A is in A, and A by construction belongs to B, because B is an open neighborhood of A in X, and this A is given to be in A, therefore this belongs to this. Yes? Are you following? Okay, therefore this is not empty. This is same as V intersection B. Are you following? Okay, please go through. I hope I am not confusing. So we have proved all these four results. Let me quickly recall. Let me write it as a theorem. Let X tau be a topological space. A is a subset of X and B is a subset of, okay, let's do that first. Okay, if A is open, okay, assume A is open, then a subset B in A is open in tau A if only open B is open in tau. Okay, it's open in the subspace topology if only. The next thing is, if B in A, B is closed in A, that is in the subspace topology if only if there is a subset C closed in X so that my B is C intersection A. I think I used F earlier, okay. And third, let's assume A is closed in X, then B in A is closed in A if only B is closed in X. And fourth, let B be a subset of A, then A be an element of A, then A is an adherent point, B in A if and only if is an adherent point of B in X. Okay, these are the set theoretic results you have to learn about subspace topology. Okay, the last one I was a little confusing because I myself lost focus, but I just wanted to show you. Okay, I'm just thinking along, therefore sometime my mind drifts away. I just wanted to show you, it can happen to anybody. Okay, so don't worry, but again rewind, okay, go back and revise, you will understand all these things. Okay, so now I'm turning my side an interesting perspective. Of a convergent sequence. Okay, let's recall. Suppose X tau a topological space, Xn is a sequence in X. Okay, then and X is an element of X. So I say Xn converges to X. This is my way of writing. I read it as Xn converges to X. Okay, I don't write limit n tend to infinity etc. because this is when I want to say Xn tends to X, that itself I want to expand. Then you are using n tends to infinity, you don't know what it is, then you want to say n tends to. Okay, so it's a kind of stupid logic. Okay, so I avoid using this. I simply say Xn. What is this by definition? Or sometimes I only write this way, limit n, not limit n tends to infinity. Notice that? Okay, this word I avoid. Okay, now you are going to see, we are going to put everything in very beautiful perspective. Okay, if and only if what happens? For every open neighborhood u of x, okay, there is a capital N, so that if k is greater than or equal to n, my xk lies in u. Okay, all of you have the picture. Okay, this is my x, x's are converging, this is my, give me any open set. Okay, what do I know? If k is greater than or equal to n, all my xk's lie here. So x, not this is my x, sorry, this is my x, all my, this will be my x case for k greater than or equal to n. They all lie there. Okay, very good. Now let us look at, okay, this is the definition. If you have not learned it, go through again, understand. This is exactly the way you define convergent sequences, real numbers or complex numbers etc. or in a metric space. Okay, good. Now let's come. Now how does it connect with subspace topology? That's a beautiful thing. I hope you love it. Let us look at the subset A, which consists of all 1 by n, as n is a natural number, along with 0. Okay, this is a subset of all. Therefore I have the subspace topology. Okay, in the earlier thing we had already seen. Okay, what are the basic neighborhoods? Yeah, for any 1 by n, the basic simplest neighborhood is singleton 1 by n, whereas when it starts with 0, the basic open set which contains 0 are of the form 1 by k, k greater than or equal to n. U means 0 course, right? These are the basic neighborhoods of in A. Okay, this we are done in the, I think the session 1 or session 2, I don't remember. We have already done that. Please go through it. If you have not done, again try to see that. Because subspace topology, this is my 0, this is my 1, half, 1/3, etc. 1 by n. Then what happens? Take any epsilon and intersect. Then what will happen? After certain stage by Archimedean property, alright, there will exist n such that 1 by n is less than epsilon. Therefore, if k is greater than or equal to n, 1 by k will be less than or equal to 1 by n, that is less than epsilon. Therefore, for k greater than or equal to n, all your 1 by k will lie in this. So these are the basic neighborhoods. Of course, it has to contain 0. Yeah, I again repeated the proof. Again, you see that pattern. What I did with a lot of elaboration and details earlier, when I want to use it today, I quickly go through the argument. This is what you have to learn. Just because you already learned, it's okay, I learned it. Don't do that. Repeat it again. Try to go through it fast so that you will become very confident. Okay, come back. Right? Now suppose xn is a sequence in a topological space. Okay? Now I want to define a function f from the set A to x. Yeah? Remember, this as a subspace topology. Right? And x as a usual topology. What is the function? Right? I am going to define f of 1 by n is xn. Remember your xn is, so you will think of this as a function from n to x, that f at n you define it to be xn. Right? Now I am defining function f at 1 by n is xn. Are you following? Therefore x, okay? Therefore I can think of xn as a sequence. Okay? Now I want to say f is continuous and assume that xn converges to x in x tau. F is continuous at 0. That is, I define f of 0 to be x. Let me quickly go through what I am assuming. I am assuming xn is a sequence in x and xn converges to x. This is my hypothesis. Okay, then what do? I define a function from a to x. How do I define? F at 1 by n is xn, f at 0 is x. Right? Then what do I want to say? I want to say f is continuous on A. Do you follow that? And f is continuous at 1 by n is very easy. Why it's very easy? Because remember, if I look at 1 by n as n varies over n as a subset of A, the subspace topology is a discrete topology. Call this as B. The subspace topology on B is not, as a subspace topology inherited from A is same as the subspace topology inherited from R. This also we have seen in session 2. Okay, it's a discrete topology. Therefore, any function from discrete topology to any space is continuous. We already know from continuity. If you don't like any of these things, I will give a direct proof. Don't bother. Okay. Let's look at xn. So what is f of 1 by n? Xn. So let V or U be an open set in tau x containing xn. Right. Then what do I have to do? I have to find an open set U containing 1 by n. This should be in tau of A, so that f of u is contained in V. This is the definition of continuity of f at 1 by n. But what is the u you will take? Remember, the most basic open sets containing 1 by n is singleton one. Therefore, take u equal to 1 by n, then f of u is of course contained in V. Yeah? Therefore, f is continuous at every 1 by n. Now let's look at continuity at 0. So here is f. Okay, pause, review, proceed. So is f continuous at 0? Okay, now let's look at. So I have my x, this is my x, so I have an open set V, okay, in tau x which contains x. To show it's continuous at 0, what do I have to do? I have to produce an open set U in tau A, so that 0 belongs to U and f of U is contained in V. Do you follow that? Yeah? Right. So this is my thing. Let me again write this. This is my 0. This is my 1 by n, this is my 1 by k, etc. And this is my 1. Okay, keep the picture in mind. So now what is the basic neighborhoods of u? Basic neighborhoods of u are of the form 1 by k, k greater than or equal to n. Do you follow that? Okay. So which u I have to choose? That is same as saying which n I have to choose. Because u depends on n. Right? But that's very easy. What is given to you? I know that xn converges to x. And V is an open set containing x. Therefore, what do I know? I know that there exists an n, so that for all k greater than or equal to n, my xk's are lying in V. Do you follow that? Therefore, I choose that n for this. Are you following? Use that n to define u. This is an open set, basic open set containing 0, union of 0. Right. Now let's look at that. So for any element x in u, f of x in v, because what is that? Either x is 1 by k, in that case f of 1 by k is xk, and k is greater than or equal to n, therefore xk lies in v, or x may be 0, in that case f of 0 is x, that's already in v. Therefore what I have shown? Therefore f is continuous on a. Pause, review, proceed. Conversely, right, let f from a tau a to x tau x be a continuous function. Okay, let x, and I am going to define the sequence now, f of 1 by n. Then what do you think I want to say about this sequence? Can you guess? Right, then the sequence xn in x converges to x. What is x? F of 0. Are you following? You are already given a continuous function from the set A, which consists of 1 by n and union 0, okay, with the subspace topology, right? And I know it's continuous. In particular, it's continuous at 0. That's what we are going to crucially use, right? So I am going to show this sequence xn converges. And where does it converge? It converges to x. What is x? F of 0. The proof is extremely easy. Okay. So I only have, this is a sequence is okay. I only have to prove it converges to f of 0. So let v be in tau and the x belong to this. Right? Okay. Right. Now, what is x? This is f of 0. What do I know of f? F is continuous at 0. Right? And now you gave me an open set of f of 0 containing, open set V containing f of 0. Therefore, by continuity, then what do I know? There is a u where in tau a, so that f of u is contained in V. Right? You understand? But if this u is an open set, what are the basic open set? Okay, there is a basic open set un, call it un. This is a basic open set 1 by k, k greater than or equal to n, union 0. Okay, therefore there exists an n, so that un is contained in u. Right? Okay. Right, what does it mean? That means start with any x in un. Therefore x is either 0. I should not say any x because there is too much of x there. Let me say a. Any a in a, that a is 0, or a is of the form 1 by k, where k is greater than or equal to n. Right? Yes or no? So what does it mean? That means f of 1 by k for k greater than or equal to n, that is your xk, that lies in V. And V is an open set containing z x. Right? So what I have shown? I have shown that, again look at the picture. This is only for your understanding. This is by 1 by n. This is r1 by k, k greater than or equal to n, right? Therefore these are all this is my un, and this is my x, this is my x which is f of 0, and this is my open set v. Therefore there is a un, so that every element here is mapped to that. That means whenever n is greater than, sorry, k is greater than or equal to n, my xk's lie here. What does that mean? The sequence xn converges to x. So intuitively you see that. So by have proved the following thing. What I have proved? Let f be any continuous function from a tau a to x tau x, okay, and define, let it this be any function, define xn equal to f of 1 by n and x equal to f of 0, right? Then this is what you prove. F is continuous at 0 if and only if the sequence xn converges to x. This is the theorem we proved. Okay, please go through, pause, review, proceed. Isn't it fantastic? So you remember, when I say xn is a sequence in a set x, that means n gets mapped to xn. Okay, it's a function from the set of natural numbers. Instead, what you are doing, you are thinking it as a function from 1 by n to x, right? My xn is the image of 1 by n in the space x, in the set x. Then 0. Now all of you have intuition, right? 1 by n goes to 0, that is clear, but n goes to infinity, you see that? So when limit n goes to infinity of xn is what you usually think of. That's the way you had been taught from 12th standard onwards. Now you see that we have very rigorous way of explaining that object. In fact, this is very useful. Please go through it carefully. When I talk about one-point compactification, I will come back to this example, and then you will understand. Everything will be very crystal clear. The role of point at infinity to deal with sequences, etc. I hope you enjoyed it. Okay, take care, stay safe. I am sure all of you are aware of Omicron wave. So, okay, take care, stay safe. We'll meet again.